Hello everybody. We are the students of BSc Honors Computer Science, third year. In this presentation, we are going to elaborate about basic interrupt processing. But before we start, I'd like to introduce you to an interrupt. What is an interrupt? An interrupt is basically a hardware initiated procedure that interrupts whatever program is currently executing. So it interrupts it, does some work, and then it continues the processing. Now we're going to talk about the basic interrupt processing, in which we are going to discuss the function of an interrupt in a microprocessor based system and the structure and features of interrupts available to the Intel family of microprocessors. It's kind of big, huh? Interrupts are particularly useful when interfacing input-output devices that provide or require data at relatively low data transfer rates. Now, interrupt processing is really important as it handles the microprocessor so that it does not sit idle to obviously prevent the time wastage. Here, we have shown the figure in which it's a timeline that indicates a typist typing a data on the keyboard, a printer removing data from the memory, and a program executing. So, the main program that is interrupted for each keystroke and each character that is to print on the printer. Now here, the keyboard interrupt service procedure called by the keyboard interrupt and the printer interrupt service procedure each take a little time to execute, but we think that the both are executing at the same moment. In this slide, we talk about the interrupt vectors. An interrupt vector contains the address, that is segment and offset of the interrupt service procedure. The types of interrupts are as follows. Type 0, that is divide error. Type 1, single step or trap. Type 2, non-maskable hardware interrupt. Type 3, 1-byte interrupt. Type 4, overflow. Type 5, bound. Type 6, invalid opcode. Type 7, coprocessor not available. Type 8, double fault. And Type 9, coprocessor segment overrun. The next is Type 10, that is invalid task state segment. Type 11, segment not present. Type 12, stack segment overrun. Type 13, general protection. Type 14, page fault. Type 16, coprocessor error. Type 17, alignment check. And Type 18, machine check. In this slide, we talk about interrupt instructions bound, into, INT, INT3 and IRET. INT and INT3 are similar. Bound and into are conditional, and IRET is a special interrupt return instruction. We can read about all 5 of them in this slide. In this slide, we talk about the operation of a real mode interrupt. When the microprocessor completes executing the current instruction, it determines whether an interrupt is active by checking first the instruction executions, second the single step, third NMI, fourth coprocessor segment overrun, fifth INTR, and sixth INT instruction in the order. Now, if one or more of these interrupt conditions are present, the following sequence of events occur as shown. Whenever an interrupt is accepted, the microprocessor stacks the contents of the flag registers CS and IP, clears both IF and TF, and jumps to the procedure addressed by the interrupt vector. After the flags are pushed onto the stack, IF and TF are cleared. These flags are returned to the state prior to the interrupt when the IRET instruction is encountered at the end of the interrupt service procedure. Therefore, if interrupts were enabled prior to the interrupt service procedure, they are automatically re-enabled by the IRET instruction at the end of the procedure. In this slide, we talk about the operation of a protected mode interrupt. In the protected mode, interrupts have exactly the same assignments as in the real mode, but the interrupt vector table is different. In place of interrupt vectors, protected mode uses a set of 256 interrupt descriptors that are stored in an interrupt descriptor table, that is IDT. We can easily see that from the figure, and we can read about the specifications as written in the slide. This slide shows the conversion from the real mode interrupt vectors into the protected mode interrupts by copying the interrupt procedure addresses from the interrupt vector table and converting them to 32-bit offset addresses that are stored in the interrupt descriptors. It's quite easy. Here we are talking about the interrupt flag bits. The interrupt flag, that is IF, and the trap flag TF are both cleared after the contents of the flag register are stacked during an interrupt. The figure here illustrates the contents of the flag register and the location of IF and TF. I would like to pinpoint that when TF is equal to 1, it causes a trap interrupt, that is type number 1, to occur after each instruction executes, which is why it is often called a single step. Trap flag allows debugging. One major difference between interrupt flag and trap flag is that the interrupt flag is set and cleared by the STI and CLI instructions respectively. However, there are no special instructions to set or clear the trap flag. With this, we come to the end of our presentation. I hope you understood the basic interrupt processing and found it useful enough. Thank you.